In this video, we're going to talk about two different types of collisions that an object or system of objects can undergo. Collisions are the natural way to familiarize ourselves with the ideas of momentum and impulse. If you're in my class, your book talks about types of collisions as far as, two objects coming together, or maybe one object exploding and breaking apart. And that's perfectly valid ways to talk about types of collisions, but it goes farther than that, which is where we're going to start to talk about the formal types of collisions. And so I'm going to write down two words here, or two phrases: perfectly elastic and perfectly inelastic. Now, when I write the words perfectly, of course, that indicates that there is such a thing as an imperfect, or maybe a not perfect collision. Imperfect is the wrong way to put that. But that is true. We're going to find out what these things mean, what these phrases mean, but there is a spectrum of types of collisions in between these two. These represent the extrema. We're going to concern ourselves in this class exclusively with these two types. So let's talk about what they mean in a perfectly elastic collision. These types of collisions conserve momentum, that is, in total momentum of the system of objects. You might find that the momentum of one of these objects that collides changes, but in fact you normally will find that, but the momentum of the system of objects stays the same. They are going to conserve momentum. They are also going to conserve kinetic energy. We're going to, again, consider the system of objects and conserve the kinetic energy. Types of these collisions, as it turns out, all collisions at the atomic level, at least those that don't result in something like nuclear fusion, just interactions between particles, all of those are perfectly elastic. They conserve the kinetic energy because there's no mechanism to take away energy. Macroscopically, how do we lose energy? Friction, sound waves, deformations in the objects, all of these things can take kinetic energy out of the system. But at the microscopic level, if you have two electrons or two protons coming together, they don't actually even touch. In fact, it's not really clear what that would mean. They interact with each other due to the forces between them. And so there's no friction, there's no sound, there's no mechanism for energy to leave the system. So perfectly elastic collisions conserve kinetic energy. Macroscopically, we actually never find a true perfectly elastic collision, but we can get pretty close. We're going to talk about billiard balls or pool balls later as a pretty good example of what is pretty close to a perfectly elastic collision. For the purposes of knowing what's what, if you lose such a small amount of kinetic energy that that loss is negligible, you can model whatever system you're looking at as a perfectly elastic collision. This is the formal definition. Any collision which conserves momentum and kinetic energy is perfectly elastic. For our purposes, here's how we identify them. The objects will bounce off of each other and move independently. Think of the last time you played pool and the cue ball hits another ball. They bounce off of each other. They don't stick together and move around as one. They move independently of each other. So this is the formal definition here. This is how we sort of identify them in everyday life. For the perfectly inelastic, this is a collision which conserves momentum, but does not conserve kinetic energy. So if the energy is not conserved, we have to ask, where does it go? Well, I mentioned earlier, things like friction, sound waves transfer energy out of an object or out of a system of objects. Lasting deformations of the objects transfer energy out of the system. So if any of those things are happening in a non-negligible manner, then you have a perfectly inelastic collision, or at least you have an inelastic collision. And for this course, we'll consider perfectly inelastic. So again, this is the formal definition. For our purposes, these objects stick together and move as one. So we're going to look at, in different videos, we're going to look at a series of examples of all of these and see if we can get some intuition for what's happening. But let's talk about these for just a little bit. So the first thing I would say is, if we conserve the momentum, if we conserve momentum, we must consider direction. Momentum is a vector. And just like we saw something like, say, an object in free fall, or go back to your projectile motion problems, which had objects in free fall. We had to consider the direction because those objects are in equilibrium in the horizontal direction, but they're not in equilibrium in the up and down direction. So just like that system could have different things going on in different dimensions, it is possible to have momentum conserved in one dimension, but not another. So if we're going to conserve the momentum, we have to examine all directions. So if we have either one of these collisions that we can truly consider perfectly elastic or perfectly inelastic, what that means is that I can get potentially three equations out of the conservation of momentum. I conserve it in the x direction, I conserve it in the y direction, I conserve it in the z direction. In this course, we're going to handle two-dimensional systems, but three-dimensional systems is just doing the same thing one more time. Just like two-dimensional systems is doing a one-dimensional problem twice. Same thing with three dimensions. So in this class, we're going to stick mainly to two-dimensional systems. But the point is, you get three equations out of the conservation of momentum because you must conserve it in every dimension. Of course, if you're going to conserve kinetic energy, that's not a vector. So the kinetic energy, if you're conserving kinetic energy in a perfectly elastic collision, that's just going to be one equation. So ostensibly, you can get four equations out of this for a system. In this class, we're going to get either two or three, depending on how many dimensions we have. Okay. Let's see an example. Oh, before we do that, let me caution you. Know what you're talking about and know what whoever's talking to you is talking about when you're talking about these. This is just a quirk of English, but anelastic sounds an awful lot like inelastic, especially when someone speaks quickly, like I have been told that I do. So make sure, if you're in my class, you're always welcome to ask for clarification on these two words, because it can be somewhat confusing. All right, so let's look at an example here of a collision in which we are not going to be able to conserve the momentum in all directions. And so this will serve as an example of what is not a perfectly elastic or perfectly inelastic collision. Take a ball and throw it against a wall. It was supposed to be a straight wall. Try to do that again. All right, let's throw it against a wall at an angle. So I have a ball of mass m, and I have some angle theta. This is traveling at some speed v. Now we know what's going to happen. The ball is going to bounce off. And we might not know, but let me just be the first to tell you, if you don't know, it will bounce off at the angle theta. When I do that, I'm ignoring any friction. So let's assume that this is a frictionless surface. So there's no friction acting along the surface of the wall. I should say maybe parallel to the wall. However, during the time of interaction between this ball and the wall, there is a force being exerted on the wall. We know that because the ball accelerates, right? It changed direction, therefore it had to accelerate. Newton's second law tells us if there's an acceleration, there's a force. What force did the acceleration? Well, it's probably not too hard to imagine that there's a normal force exerted from the wall onto the ball. So if this is what I'm looking at, and if we ignore gravity here, let's assume that either gravity's not acting here, we're out in space, or that I have gravity oriented up and down, so it doesn't really come into my consideration of this motion. However, whatever gets you there. We're ignoring gravity. And so if I do a free body diagram of this ball, as it's impacting the wall, it really just looks like this. I've already told you to ignore friction. So there is a force in the horizontal direction, but not in the up and down direction. Well, what that means is that I can write this down, T initial to T final, the normal force dt, but which you might recognize as the impulse equation, right? This is how I determine the impulse acting on an object. But this is a vector, and this force is all in the x direction in this case, how I've drawn it, which means the impulse is all in the x direction. Now, if there's an external impulse to the system, if I consider the system to be just the ball, this represents an external impulse, and momentum is not conserved in that direction. So, as we've written the conservation of momentum, what we've said is in the absence of an external impulse, an object's momentum remains constant. This would represent an external impulse to the system, but because this force is only acting in the x direction, there is an x component of the impulse. There's no y component of the impulse. There's no z, if you want to be complete, component of the impulse. It's just in the x direction. So what we'll say is that momentum is conserved in the directions for which there's no external impulse, not conserved here. To handle the x direction, I've got to go through impulse momentum. To handle the y direction, which is the only other one I have acting here, if we call this y, I can find the final velocity of the ball just by, or at least in the y direction, just by conserving the momentum. And you might be able to see that there has to be no change in the velocity, at least in the y direction of this ball, because there is, the momentum is conserved. So that's just an example of a collision which we wouldn't really be able to handle in all dimensions with conservation laws. We can't say that the momentum is conserved in the x direction. In the y direction, absolutely. Use all the conservation you want. But in the x direction, you're going to have to go through impulse momentum, which we've already looked at. All right. So those are collisions in multiple dimensions and collisions in general. And so we're going to develop some examples from these ideas in future videos, similar to what we did with conservation of energy, to try to give us some intuition about how this works.